Every time you ask an AI to write an email, generate an image, or answer a question, the result feels weightless. It arrives from the cloud. But the cloud is not weightless. It is a building. Sometimes many buildings, rows of servers, cooling systems, backup generators, substations, and power lines that have to be ready before you press send. The question is no longer just whether AI uses electricity. Of course it does. The harder question is this: when a new data center needs enough power to change an entire region's grid plan, who pays for the new wires, the new capacity, and the backup power? The company building it? The utility? The taxpayer? Or the family opening an electricity bill months later? This is the hidden cost of the AI boom. And the honest answer is more complicated than either side of the argument wants it to be. For years, electricity systems in wealthy countries were built around a fairly predictable pattern. Homes used more power in the morning and evening. Businesses used power during the day. Factories used a lot, but demand usually changed slowly enough for utilities to plan years ahead. Then came data centers. A modern data center is not simply an office with more computers. It can be a huge, continuous industrial load. It needs electricity around the clock. It may need cooling during heat waves, when the rest of the grid is already stressed. And it cannot casually accept an outage because the weather is difficult. AI adds another complication. Training and running large models can require more specialized chips and more computation concentrated in fewer places. The International Energy Agency projects that global data center electricity consumption could more than double to around 945 terawatt-hours by 2030. In its U.S. outlook, data centers account for nearly half of projected electricity demand growth through the end of the decade. That does not mean one AI question directly builds one new power plant. Electricity systems do not work one prompt at a time. But it does mean millions of digital actions are turning into physical demands: substations, transformers, transmission lines, power plants, batteries, land, water, and construction crews. To understand the fight, separate three things that are often mixed together. First, energy. This is the electricity flowing through the wire at a particular moment. A data center buys it, just like a factory or a home does. Second, capacity. The grid has to be ready for the moments of highest demand, not just the average day. If a data center expects to draw a huge amount of power on a hot summer evening, the system needs enough generation, transmission, and backup to serve it when conditions are difficult. Third, network upgrades. A power plant may exist somewhere in the region, but that does not mean electricity can reach a new campus safely. The grid may need a larger substation, a new transformer, upgraded transmission lines, or local distribution equipment. One building can therefore create several different bills. The bill for energy now. The bill for enough capacity later. And the bill for the wires and equipment that make the connection possible. Who receives each bill is where the politics begin. Imagine a fictional town called Northfield. An AI developer wants to build a giant data center campus outside town. It promises construction jobs, tax revenue, and a technology hub. The local utility welcomes the investment. Local politicians like the jobs. The region wants the prestige of hosting the next wave of computing. But the existing substation is too small. The nearest transmission line is already heavily used. A transformer could take years to obtain. Engineers say the project might also require upgrades farther away, because a huge new load changes how power moves through the network. Now the costs split into different paths. The developer might pay for the dedicated line into its own campus. The utility might pay for upgrades it says will benefit the wider grid. A regional grid operator might spread some transmission costs across several utilities. And the utility may later ask its regulator to recover approved spending through customer rates. The physical upgrade is the same, but its description changes depending on who is speaking. The developer may call it a public grid improvement. A consumer advocate may call it a cost shift. The utility may call it necessary reliability investment. The regulator has to decide which costs were directly caused by the new customer, which ones serve everyone, and which ones are reasonable to recover from ordinary users. This is why the phrase, "the data center pays for everything," can be misleading. But so can the opposite claim, "households are definitely paying for AI." Both statements can be incomplete. The answer depends on the local grid, the tariff, the utility contract, the regulator, and what infrastructure would have been needed anyway. A large customer may fund dedicated equipment. It may sign a long-term contract for new generation. It may agree to reduce demand during rare grid emergencies. It may even locate near existing generation. Those choices can reduce strain on the system. But they are not automatic. A renewable energy contract is not necessarily the same thing as new local electricity at the moment the grid needs it. A public promise is not the same thing as an enforceable tariff. And a connection fee may not cover every shared upgrade outside a project boundary. The key principle is cost causation. If a specific project requires a specific upgrade, the public should be able to see that link. If an upgrade genuinely serves the whole region, the public should be able to see that too. Without that transparency, ordinary customers are asked to trust a system they cannot inspect. This is no longer a local planning argument. In June 2026, the U.S. Federal Energy Regulatory Commission told 6 regional grid operators to justify or reform rules governing large new electricity users, including data centers. Its stated concerns included cost shifting and transparency around transmission costs. In Great Britain, Ofgem is examining how to connect large new demand faster while protecting consumers. It has warned that rapidly growing, poorly located demand, such as data centers, can increase network reinforcement and constraint costs that are ultimately largely borne by consumers. The wording is important. Regulators are not saying every data center is a bad project. They are saying old rules built for gradual demand growth may not be enough for a few giant new customers. The problem is speed. Digital companies can make investment decisions quickly. Physical grids move slowly. They need land rights, engineering studies, equipment orders, public hearings, financing, and construction. When private demand arrives faster than public infrastructure can respond, the queue itself becomes valuable. In a fast-growing region, developers may request more capacity than they ultimately build. They want a place in line. They want options. They want land and electricity before a competitor gets there first. But the grid has to plan around those requests. That can clog connection queues and distort forecasts. A system may prepare for projects that never arrive, while serious projects wait behind them. It is a kind of digital land rush, not only for land, but for access to electricity. A better queue would ask harder questions. Is the project financed? Is the site credible? Can it reduce demand during emergencies? Is it located where the grid can serve it efficiently? What happens if it cancels after the network has spent money preparing for it? Those are not anti-technology questions. They are infrastructure questions. The details change across countries, but the tension is spreading. In the United States, EIA forecasts the strongest four-year electricity demand growth since 2000, with large computing facilities among the major drivers. In Australia, the grid operator projects rapid data center demand growth in its national electricity market scenarios. In Canada, the energy regulator is modeling a wide range of future data center load because the sector is large, fast-moving, and uncertain. These are not identical markets. They do not use the same tariffs or the same regulatory institutions. But they face a shared challenge. Private computing demand is growing faster than the old assumption that electricity demand changes slowly. The easy slogan is, "Make big tech pay." The serious version is harder. First, regulators need transparent accounting. Customers should be able to distinguish direct project costs from shared grid investments. Second, connection queues should reward credible projects rather than speculative reservations. Third, large new loads should have clear incentives to locate where the grid can serve them efficiently, instead of forcing expensive upgrades in the most constrained places. Fourth, flexibility should be real. If a data center claims it can reduce demand during an emergency, the agreement should be measurable and enforceable. And finally, the public should see both sides of the ledger: jobs, tax revenue, new generation, reliability benefits, and the full infrastructure costs needed to make them possible. None of these ideas guarantees lower bills. But they make hidden decisions visible. The AI boom is often described as a race for chips. It is also a race for electricity. Advanced models need computing power. Computing power needs data centers. Data centers need land, equipment, permits, workers, and above all, reliable electricity. That means the future of AI will not be decided only inside software companies. It will also be decided in utility commission hearings, grid operator meetings, local zoning fights, and transmission planning documents. The cloud is becoming a public infrastructure question. So the question is not simply whether AI uses electricity. Of course it does. Ask instead, when a new digital industry needs the grid to grow, who owns the upside? Who carries the risk? And when the bill arrives, can the public see who really paid? Because behind every invisible AI answer is a very physical system. And somebody has to fund it.